Hello. In this video, we'll dive into convolutional neural networks, CNNs, using PyTorch. Instead of focusing on theory or complicated visualizations, we're taking a hands-on approach to build a CNN from scratch. We'll focus on practical code implementation in the PyTorch framework. We're working in a Google Colab notebook environment. While you can certainly use a CPU runtime for this tutorial, we'll opt for a GPU to speed things up and make our training more efficient. Let's start by importing the libraries we need. We'll primarily need PyTorch and some of its submodules, along with pandas for data exploration and analysis. With our imports ready, we can move on to downloading our dataset. For this tutorial, we'll use the Sign Language MNIST dataset. This dataset contains images of American Sign Language letters, which makes it perfect for our image classification task. To download this dataset, we'll import Kaggle Hub and use the dataset ID to download it. At around 62 megabytes, this is a manageable dataset that won't take up too much disk space. Once the dataset is downloaded, we'll create pandas data frames for both our training and validation data. We'll locate the CSV files in our path and read them into pandas. These CSV files contain our image data and their corresponding labels. Now let's set up our dataset and downloader constructs. First, we should define some constants. Our images are 28 pixels by 28 pixels and have a single channel since they're grayscale images. Next, we'll create a custom dataset class by subclassing PyTorch's dataset class. Let's call it Sign Dataset for our sign language data. In the initialization function, we'll handle pre-processing by extracting the images and labels from our data frame, normalizing the pixel values, and reshaping them appropriately. This reshaping is crucial because while our data might initially be stored as a flat vector of pixel values, we need to reshape it to match the actual image dimensions for our convolutional operations. We'll convert our data to PyTorch tensors and make sure to move them to our CUDA device if we're using a GPU. Also part of our dataset class, we also need to implement the getItem method, which returns the image and label at a given index. Since the length of our images and labels collections are the same, we can simply return the length of our images for the len method. With our dataset ready, we can create a data loader using PyTorch's built-in data loader class. We'll specify an appropriate batch size to efficiently process multiple images at once during training. Now we're ready to define our convolutional neural network model. PyTorch's high-level abstractions make this relatively straightforward. Let's start by defining some constants, including our kernel size for the convolutions. We'll build a sequential model using PyTorch's neural network modules. For our first convolution layer, we'll use the conv2d class and specify parameters like kernel size, stride, and padding. After the convolution, we'll apply batch normalization using the 2D method since we're working with 2D images. This helps standardize the inputs to each layer, making our network more stable during training. For activation, we'll use a rectified linear unit, or ReLU, which introduces nonlinearity to our model. After activation, we'll apply max pooling, which reduces the spatial dimensions of our feature maps while preserving the most important information. After our first convolutional block, we'll add a second similar block, but with an important addition, a dropout layer. Dropout randomly sets some neurons to 0 during training, which helps prevent overfitting by ensuring that no single neuron becomes too influential in our model's predictions. This makes our model more robust and generalizable. For our second convolution layer, we'll keep the same pattern of batch normalization, ReLU activation, and max pooling, but we'll increase the number of feature maps from 25 to 50. This allows our model to detect more complex patterns in the input images. Let's add a third convolutional layer, further increasing our feature maps to 75. After these three convolutional blocks, we'll need to flatten our output. This flattening operation transforms our multi-dimensional feature maps into a one-dimensional vector that can be fed into a fully connected layer for final classification. Now that we've defined our architecture, let's take a moment to understand what's happening in our model. Our goal is to gradually reduce the dimensionality of our input while extracting meaningful features. We start with a 28 by 28 pixel grayscale image, one channel, and apply convolutional filters to create 25 feature maps. Due to our max pooling operation with the kernel size of 2, we reduce the spatial dimensions by half after each layer. So after the first convolution of max pooling, our 28 by 28 pixel image becomes a 14 by 14. After the second block, it's reduced to 7 by 7, and after the third block, it becomes 3 by 3. We then flatten these 75 feature maps in size 3 by 3 into a one-dimensional vector, which feeds into our fully connected layer to produce the final output for our 24 classes. Now let's compile and run our model. We'll make sure to push the model to our GPU for better performance. For our loss function, we'll use the standard cross-entropy loss, which is appropriate for multi-class classification problems. For optimization, we'll use the atom optimizer, which adaptively adjusts the learning rate for each parameter. To measure our model's performance, we need to create a few functions. One to calculate batch accuracy, one for training, and one for validation. Once we have these functions defined, we can run our training loop. Training will take some time, so we can monitor GPU utilization by clicking on the button in the top right corner of the Colab interface. As we begin training, we might encounter an error related to our architecture. These errors often occur due to tensor shape mismatches, which is a common issue when defining neural network architectures. Let's debug our model by checking the number of classes in our dataset. It looks like we actually have 25 classes in total, not 24 as we initially assumed. After adjusting this and rerunning our code, things should work better. With the tensor shape mismatches fixed, we can now see the training loss dropping rapidly and the validation accuracy stabilizing at around 98%. This high accuracy indicates that our model is performing well on the task. As training progresses, we might notice that even though our training loss continues to decrease, our validation metrics don't improve much after a certain point. This suggests that we might be starting to overfit to our training data around the 8 to 10 epoch mark. Overfitting happens when a model learns the training data too well, including its noise and peculiarities, which doesn't generalize well to new, unseen data. However, even after 20 epochs, we still have reasonably good metrics on both our training and validation sets, suggesting that our model isn't severely overfitted. The entire training process took about a minute and 45 seconds with our GPU. Congratulations! We've successfully built and trained a convolutional neural network from scratch using PyTorch. This model can now accurately recognize American Sign Language letters from images with high accuracy. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. If you have any questions, please post them in the comment section, and we'll do our best to respond. Thank you very much for watching to the end, and please enjoy responsibly.